Thanks so much, Carly. So now we're going to hear from Carolyn Mercer, who is Chief Technologist at NASA's Science Mission Directorate at NASA headquarters, who's going to talk to us about the challenges of exploring the outer solar system.
Thank you very much. And I am so happy to be here. Thank you so much for the invitation, for coming out here. If we can get my title slide here, I'm going to be talking about innovative technology to get to the outer solar system. And thanks so much, Carly. Oh, I'm the one that's controlling it. Right, okay. There we go. So thank you so much, Carly, for setting the stage, because the science is what we are trying to do. It's all about the science, and so getting to the outer solar system really matters a lot to me personally and to NASA. At NASA, we have three key science themes: protect and improve life on Earth and in space, search for life elsewhere, and discover the secrets of the universe. Of course, this community is really interested in searching for life elsewhere, but I want to say that these three themes are not mutually exclusive. Particularly the technologies that we're developing for them, they're cross-cutting, and particularly for getting to the outer planets. So what I want to do is tell you about, very quickly, three missions that we have either recently done or in the process of doing, future missions to the outer planets, and then technology that I think can really rock our world and how we might get to the outer planets. So the first of the three missions that I want to tell you about is protecting life on Earth, and that is the amazing double asteroid redirect test mission. Perhaps you're all familiar with it. It's one of my favorite missions. Humanity, for the first time, has altered the course of a planetary body, an extraterrestrial body. So the DART spacecraft intentionally crashed into the smaller of an asteroid pair. And so before DART arrived, Didymos was orbiting Dimorphos with a period of about 12 hours. And now it's orbiting at about 11 and a half hours. That's amazing, right? And the technologies that we used included a nice ion electric propulsion system and some solar concentrators that will allow us to use solar energy farther out into the solar system. Now, I want to say that deflecting asteroids is more effective the farther out in the solar system you are. So perhaps we will have need someday for getting out to the outer solar system quickly in order to do a deflection. Second mission is Dragonfly, which is in development right now. And it is going to go to Saturn's moon Titan, that we've heard a little bit about during the last 2 days here. And it is an octocopter, right, that is going to fly. It is going to be released from its spacecraft, enter the atmosphere flying, autonomously land, collect samples, analyze them, and then take off and go to another cycle, rinse and repeat. It's an amazing mission, and Ingenuity is the first aircraft that has flown on another planet. We expect that it's going to be substantially easier to fly on Titan because the gravity's lower and the air density is thicker. So technology is absolutely changing the way that we're exploring this outer world. And then the last one is Europa. Europa Clipper is going to launch soon. And we've heard a lot about that in the last couple days, right? Liquid ocean water, hydrothermal vents, energy. I would also add to that is that several kilometer layer of thickness of ice is providing radiation protection for whatever life might be in that ocean. So it's an amazing mission, and I can't wait to find out what they're going to be discovering. So for the future, within NASA, right, every 10 years we go to our national academies of science and ask them what the next priority should be. And so for planetary science, they made 2 recommendations. First of all, finish the flagship missions that we already have. But the next flagship mission should be a mission to Uranus, specifically a mission called the Uranus Orbiter and Probe. And after that, it's the Enceladus Orbilander. These are both missions to the outer planets, in large part because of that graph that Carly showed, right? We don't have any missions to those destinations. So this is an amazing photograph that the James Webb Space Telescope took of Uranus. And Uranus and Neptune are one of the least explored, or the 2 least explored planets in our solar system. Uranus is an incredible planet. It's tilted at its side, much more so than other planets. It's got a crazy magnetic field. We don't know what its composition is. We don't know how it formed. And studying Uranus can give us insights into understanding exoplanets as we're discovering them. And then Enceladus, as we've heard a lot about today, is also a fascinating destination. So I think we've talked enough about that I'll go ahead and move on. So let's go back to the Uranus Orbiter probe. So the nominal configuration, which was proposed to the decadal and selected as the destination, was done by Amy Simon and her team. And I picked out the particular features that I'm showing here. Right, first of all, it's far, going to Uranus is far away. With a launch date in June 2031, it's going to take somewhere between 12 and 15 years to get there. Now, that's a problem. That's a really long time. And maybe that's one of the reasons why we're not doing a lot of outer solar system missions. Because if it takes that long, number one, it's expensive. And number two, we have so few opportunities to go that we tend to pile on all kinds of things to make sure that once we're there, we do all that we can. Part of the reason that it takes so long is because in order to do, if we just wanted to do a flyby, we could get there faster. But if we want to go into orbit around Uranus, we actually have to throttle our speed back on the way to get there so that our velocity is low enough that we can do an orbital insertion. And you can see that the mass of this spacecraft, 60% of the mass is the propellant on this thing in order to do that slow down and get into orbit. And a total of 1 kilometer per second of that is for orbit insertion. So two of the key technologies I want to talk about right now are ways that we can get to the outer planets faster. The first one is aerocapture. So aerocapture essentially says that you can enter into the atmosphere of a planet and use the atmosphere itself to slow your spacecraft down in one pass. We've done aerobraking before at Mars, but we've never done aerocapture, which will let you reduce the trip time by getting to that planet faster and slowing down by using the aerothermal forces on the spacecraft. And so a study that was done recently shows that you could get there in 7 to 9 years and save a full ton of fuel, which you could use to carry extra payloads. Another technology that is being developed faster than you might think is nuclear propulsion. And there's nuclear electric propulsion, there's nuclear thermal propulsion. The study here shows nuclear electric propulsion could get to Uranus in about 10 years with a nominally the same size payload. If you wanted to carry a whole lot more payload, you can get like 3 tons in 14 years. So for aerocapture, the decadal actually called out and had a finding on aerocapture. And they describe what aerocapture is there. But they also make the statement, aerocapture is a technology that is ready for infusion. Let's go. So if it's ready for infusion, how come it's not being proposed? So we asked that question. And what we did was we got a team of scientists together and said, if aerocapture is such a good thing for these outer planets missions, what are the barriers? Why aren't we using them? And what they came back with was, number one, we don't understand the atmospheres. And so it's really a lot of uncertainty in how that aerothermal loading would work. But number two, we have never demonstrated this technology. And saying it's ready and proving it's ready are two different things. And so we had them assess whether or not it would make sense to have an Earth-based aerocapture demonstration using a small spacecraft. And their conclusion was, yes, it would absolutely make sense. And so now I am absolutely advocating for a small-sat aerocapture mission into Earth's atmosphere. And we would learn several things. We would learn the performance of the thermal protection system. We would learn about autonomous optical navigation and develop control actuators. And not least, we would learn whether our models are accurate or not. And so we could learn whether or not the aerothermal loading is correct, what do we predict it accurately, and the so-called numerical predictor-corrector algorithms that would be used to feed into the guidance system. So I'm very hopeful that we will get to do such a mission. Similarly, we stood up another team because autonomous navigation, is something that we should be able to be using a lot more of, and yet we're not. And so they're actually going to be reporting out next week, but I think that they're going to come to the conclusion we should do a technology demonstration for autonomous navigation too, because on these multi-year missions out to the outer planets, if you have a team of people that have to be operating that mission, that really contributes to the cost. So anything we can do to automate that could make it easier for us to do these missions. So for nuclear propulsion, the Decadal also had something to say about that. And basically they said that flight times can really be reduced using this technology, and we should pay attention to it. So what I want to tell you is there is a lot of activity going on outside of the science community right now in both nuclear power and nuclear propulsion. Nuclear power is important because, for one thing, the Artemis mission going to the moon, setting up an outpost, they need a lot of power, and a fission reactor is absolutely the right way to go to get a sustainable, continuous, large amount of power on that surface. So they are planning, they are putting money in, and they are going to build a 10 kilowatt reactor that's going to go up there. This matters to us because a fission reactor is the power source for a nuclear electric propulsion system. So the DART mission had an electric thruster on it. You couple an electric thruster with a nuclear power system, and you have nuclear electric propulsion. Nuclear thermal propulsion is now a really big deal for the US Space Force. And so the Space Force and NASA are teaming together and putting substantial amounts of money to do a flight demonstration called Draco. It's going to fly in just a couple of years. And then lastly, the Space Force alone is doing 2 demonstrations for nuclear electric propulsion, both a small version and a large version. So, I'm not sure in the science community how aware we are of what's going on. This is coming sooner than we think, and it is absolutely going to change the way we're doing business. There's just a few more technologies that I want to talk about that I think are going to change the way we do all of our missions, not just out-of-planet missions. And the first is high-performance space computing. So right now in San Jose, there's an IEEE conference where a company called Microchip is announcing its product called HPSC that was a public-private partnership with NASA to get radiation-hardened electronics that are high performance. We have been using the RAD 750 for a very long time. Advanced computing has changed every industry but ours. This finally is going to change what we are going to be able to do. With high-performance computing on board, we can now do a lot more sophisticated onboard processing, including AI, but at least autonomy, right? We're not even doing autonomous onboard data processing right now. And then lastly, high data rate communications. You may know that the Psyche mission to the asteroid belt carried with it a technology demonstration called Deep Space Optical Comm. They are now around Mars. They're at about 2.8 AU, and they are delivering data back from Mars at 6 megabits per second, using 2 watts, right? Let that sink in. That is a lot of data for a small amount of power. It's working great, and that same type of system put on a mission like the Uranus Orbiter probe, we estimate could bring back 1 to 10 megabits per second for the same power and same volume as the spacecraft or as the communication system that's being planned for that mission. So one thing I will say, and I should have said when I showed the Uranus Orbiter probe slide, the Uranus Orbiter probe is being discussed and it's being talked about without the consideration of any of the technologies that I'm talking about here, right? So don't get me wrong, I am not saying that any of this is going to be infused into that mission. But I was asked to say a provocative statement. Let me say that that is a provocative statement. Why is it that we have missions that are still in pre-formulation, that are so hesitant to to even say that they will consider putting new technologies on no matter how close they are to being ready. So that's one of the things that I care about a lot, and am trying to make sure that these missions that go out there very infrequently carry with them the best of what we can do to return science. And so in summary, we've got landers and probes to outer planets. They're a high priority for future science missions. Both aero capture and nuclear propulsion can substantially reduce trip times to the outer planets if we only use them. And the amount of data returned is, of course, the true measure of science efficacy. And onboard data processing and high data rate communications are key to increasing that science return. So that's what I wanted to tell you about. Thank you very much for the time.